All right, so now let's look at the conservation of energy for symplectic methods. Okay, so if you have a Hamiltonian system, say dz dt is equal to this symplectic matrix times the gradient with respect to z of the Hamiltonian, okay, and a symplectic discretization then what we showed was that the modified vector field in the sense of backward error analysis is Hamiltonian. Okay. So to be a little bit more precise, the vector field's only locally Hamiltonian, right? Okay, but in some cases it's like that modified vector field is actually globally Hamiltonian. Okay, but the modified Hamiltonian is globally Hamiltonian. Oh, well, it's global, right, for symplectic splittings. Methods and all symplectic integrator, and all symplectic recursive methods. Okay. Right. So, so let's look at a very specific case. It's like in order to try to say something about the near conservation of energy. So in the case that all the involved functions are real analytic and bounded, okay, then the difference between the numerical method and the flow of the optimally truncated modified equation can be made to be exponentially small. So we discussed this to a little bit. It's like when we talked about backward error analysis. So the difference between the numerical method and the flow of this optimally truncated modified equation. If you recall, it's like what I had called F tilde I star, right? Can be made exponentially small. All right, so that's sort of the setting which we have in mind. It's like we're going to look at a Hamiltonian system. We're going to apply a symplectic integrator to it. We're going to do backward error analysis, and we're going to look at this optimally truncated Hamiltonian, this modified Hamiltonian, which is very, very close. It's like to the symplectic integrator itself, and the error is exponentially small respect to the time step. Okay. So let's see what happens. Okay. So let's denote this modified Hamiltonian by H tilde, and there's a H dependence. Then what happens is that for a symplectic integrator, of order p greater than or equal to 1, right, we have that the difference between the Hamiltonian and the modified Hamiltonian is big O of h to the p. Okay. All right. And if you recall, this has we showed this again. It has something to do with interpreting the modified equation. It's like in terms of a modified Hamiltonian. Okay. So let's look at what happens to this modified Hamiltonian. It's like as you compute this over numerous time steps. So let us investigate the conservation of the modified Hamiltonian along sort of numerically computed solutions. After n steps, right? So you might ask, it's like, well, why do we do this? And of course, if the modified Hamiltonian was actually corresponding, it's like to, it's like if this asymptotic series, it's like actually converged, right? Then you wouldn't have to, it's like, take much effort to do this, because then what that would basically say is that the symplectic integrator was honest to goodness the time h flow of a modified Hamiltonian, okay? And so as a consequence, the modified Hamiltonian would be exactly preserved along the numerical solution trajectory. But of course, what's happening here is that you don't actually have this asymptotic series that's like converging. All you have is that the modified Hamiltonian is the one you get when you optimally truncate this. And so the error is very small, but it's not zero. And so in particular, you don't expect the symplectic integrator to exactly preserve this optimally truncated, optimal sort of modified Hamiltonian. Okay, so that's why there's a little bit of work to be done here. Okay, so let's just see what happens. All right, so you look at the modified Hamiltonian evaluated at this time n. Okay, and again, the modified Hamiltonian depends on the time step h, and you want to look at the difference between that and the modified Hamiltonian at the initial time, okay, or the initial data, if you will. So that's what you're trying to estimate, okay. And what you can do, of course, is that you can bound this. It's like by expanding. It's like this term. It's like in a telescoping series, and then it's like using the triangle inequality. So that's what we do, okay. So this is less than or equal to the sum from I equals to 1 to n, okay. Then now it's like I'm just taking the change in the modified Hamiltonian over one time step, okay. Okay, and of course it's like you get this, it's like by sort of adding and subtracting, it's like these intermediate values of the modified Hamiltonian, it's like in the interior points. And then again applying the triangle inequality. Okay, so then the next thing you do is that you do the following. So this is less than equal to, so I'm going to write Zi as the one-step method applied to Zi minus 1. Okay, so this is less than equal to I equals 1 to n, right? H tilde, okay, the one-step method applied to Zi minus 1 on the one hand. All right, and then here, right, I'm going to use the fact that the modified Hamiltonian is a constant of the exact flow associated with the modified vector field. Okay, so this is minus H tilde, okay, the exact flow map of the modified Hamiltonian, right, of the modified Hamiltonian vector field, if you will. Okay, so this is applied to Zi minus 1, okay, and then you take the absolute values. Okay, so now it's like the next thing you do is that you assume that the modified Hamiltonian is Lipschitz, so I rewrite this just in terms of the difference of the values I'm evaluating it at. Okay, so this is less than equal to the sum from I equals 1 to n of some Lipschitz constant of the modified Hamiltonian times the difference between these two flows applied to the same point. Okay, so this is the numerical, this is the symplectic integrator, and then this is the exact time h flow of the modified vector field. Okay. All right, and then we have an estimate for this. Okay, that these things are sort of exponentially small. Okay, so this is less than equal to 3 lambda nhc1 e to the minus gamma over h. And you know, again, this has to do with this exponentially small error. Okay, so where your lambda greater than 0 is the Lipschitz constant for h tilde, right? And we also use the fact that h tilde of h is the first integral of the modified vector field. F tilde of h. Okay, so again, it's like going from this term to this term uses the fact that h tilde is a first integral of this flow map. Okay, so let me just write that explicitly. H tilde Zi minus 1, h is equal to h tilde, the flow of the time h flow, it's like of the modified vector field applied to the data. Okay. All right. So what that more or less tells you then is that the change in the modified Hamiltonian, it's like along this numerical solution, it's like generated by the symplectic iterator, is again exponentially small in the time step. Okay, so let's in h tilde h remains exponentially small. Over exponentially long times. And so, for example, if you have Tn, which is of course n times h, is less than equal to e to the gamma over 2h, right? If you had that kind of total time, it's like then your nh here will be replaced by e to the gamma over 2h. It's like multiplied by e to the minus gamma over h, so you still get a e to the minus gamma over 2h term, right? So yeah, so as long as you it's like stay within this sort of exponentially large time interval, then the error remains exponentially small. Okay? All right, so this implies that the conservation over the given Hamiltonian, so this is the original Hamiltonian, h, conservation of the given Hamiltonian h over exponentially long times sort of up to an error which is sort of big O of h to the p. Okay, and the reason, of course, is that the original Hamiltonian, right, is big O of h to the p close to the modified Hamiltonian. The modified Hamiltonian is preserved sort of to exponentially small error. It's like over exponentially large times. So basically then if you again do this exponentially large time thing, the worse it's like which the true value of the Hamiltonian function can drift, it's like over your symplectic integrator solution, right, is this error which is big O of h to the p. Okay, all right. So let's see this more carefully. Okay, and all right, so